Hello everyone! Let's see what do we have this time. Copy and complete this mapping diagram. I already copied it, so that part is done, and now we have to actually complete this thing. So what this does is basically it multiplies everything by 2. So this is what we call an input. This is what we call an input. This is what we call an output. It goes from here and then it goes like this, right? And then bam, it gets multiplied by 2. So whatever comes in there gets multiplied by 2 and then it comes out, kind of. So if we take 1 in there, so what we have to do is we have to do 1 times 2, and the result is going to be, of course, 2. If we take 2 inside of this thing, we will get 4 as an answer. If we get 3, we would get 6 as an answer. This is called a mapping diagram. Maybe we should do a bit more of them. I think there should be more examples. Okay, this is more interesting actually. I think maybe I can show more about how it works from this example. So let's do them right next to each other like this. Okay, and now what we're supposed to do is, you see, now we have 2 actions. So whatever comes in there, it has to be multiplied by 2, 1, and then it has to be, we have to add 7 to it as well. So we do 1 times 2, and then plus 7. And the answer is going to be 9 in this case. Then we do 2 times 2 and plus 7, which would give us 11. 3 times 2 plus 7 gives us 13. 4 times 2 plus 7, I think you can guess it already, it gives us 15. And 5 times 2 plus 7 would give us 17. Okay, so this is kind of like an introduction to the function machines, and later you will see more questions related to this topic. And next thing we have a table. So it's called a table of values for equation, and we use it normally to draw a graph, which we will also do today, but a little bit later. So table of values, let's do it as well. Copy and complete the table for each equation, then draw the line. There's actually a lot of them. Actually, wait, let me pick up the other one. Oh, we have also a diagram. Okay, let's do number 3 first. Since I started talking about the tables already. So this is something we use to draw equations. Let's take it in here. Yeah, okay, and the first one we have is y equals 2x plus 5. So what we have to do is we have to draw this table x, y, and then we have different values for x, which are -1, 0, 1, and 2, 4 of them all together. And what we have to do, how do we get y? Okay, so what we have to do is we take -1, x equals -1. So we take this -1 and we put this into this equation. So instead of x, we will get -1 here. And then y becomes, y is going to be 2 times -1 plus 5. So that's -2 plus 5, which gives us actually 3. Next one here we have 2 times 0, because x is 0. So again, instead of x, we get 0 in here. So it's going to be 2 times 0 plus 5 this time. 2 times 0 plus 5 equals to 5. Next one we do 2 times 1. 2 times 1. So you see how it happens. We do 2 times -1 plus 5. Then we do 2 times 0 plus 5. And then we do 2 times 1 plus 5, and we finally do 2 times 2 plus 5. So this is, normally this is x, right? But we change it depending on the value of x in this table. So then next one is going to be 2 times 1 plus 5 is 7, and 2 times 2 plus 5 is equal to 9. Okay, now we can draw the graph. Let's draw a small graph like this. I hope I can fit everything. Actually, no, because we have y 9, so I can already see we're not going to fit it there. So maybe it's better to do it like this. Yeah, because we don't really have a lot of negative values. It's mostly positive y. Mostly positive. So we start with x minus 1, and again this is our points. You see, each pair of x and y is going to be a point from now on. So this, for example, this becomes a point minus 1, 3, right? This becomes a point 0, 5. This becomes a point, let me take it like this, 1, 7, and then finally we have point 2, 9, like this. And now we can draw all of these points. So we go minus 1, 3. So first, of course, we have to draw a scale. We can draw a scale here. Minus 1, 0, 1, 2, 3, and y goes 1, 2, 3, 4, 5, 6, 7, 8, and finally 9 somewhere here. Okay, so minus 1, 3, how do we draw this point? Minus 1 here, so x is minus 1, y is 3. So they meet together, they will meet here at this point. So minus 1, 3 is here, and then we go 0, 5. I think I'm going to use red one for this. So minus 1, 3, then we have 0, 5, then we have 1, 7, and finally we have somewhere here we have 2, 9. Okay, so now that we have these points, what you can do is, if you have a paper, you can take a ruler and you can draw a line which goes through all 4 of these points. I will try to do it without ruler. I hope it works for me. Yeah, something like this. Also, it's nice to give a label to your line, and the label is, in this case, okay, let me write it here. The label is y equals 2x plus 5. This is our label. Okay, and let's do a second one as well. So second one is y equals 2. Y equals to 3x minus 2. And alright, so now we do the similar thing. We also do a table of values as well. I hope I have enough space here. Or maybe I should just go to next page. Yeah, I think I will do that. I have, my notebook is infinite after all. I can use as many pages as I want. Hey, hey! As many pages as I want. So table of values first. So we have x and y, and we are told in this question that we have to put these values to be x. So it's minus 1, 0, 1, and then 2. This is our x values. And we do the same thing as we did before. So we just take these values, we take minus 1, and we put it into this equation. We replace x with minus 1. And then the result we're going to get is going to be 3 times minus 1, minus 2. So that's minus 3 minus 2, which is equal to negative 5. Then we have a negative 2. You can check this. So we do 3 times 0 minus 2 equals to negative 2. Here we do 3 times 1 minus 2, which is equal to 1. and here we do 3 times 2 minus 2. So again, 2 comes from here, right? This is where it comes from. We replace x with 2. So 3 times 2 minus 2 is equal to 4. And now we can draw the graph. So we have a lot of negative values as well. So this time I will leave some space for a negative y. I think here, yeah, this would be probably nice. So this is our y and this is our x. We can do some labels. Yeah, something like this. You see, I don't put a lot of labels for x because I know that our points are only in this range. So it's from -1 to 2, only here. But you can put more points to make it look nice if you have some extra time. So -1, -5, this point is here. So -1, x is equal to -1. Again, this point. X is -1, y is -5. So -1, -5, it's here. Next one we have is 0 minus 2, so x equals 0, y equals -2. This point is here. 1, 1 is here. And then 2, 4 is going to be here. And again, you should take your ruler and draw a line which passes all 4 of these points. We can label this line as y equals 3x minus 2. Okay, that's drawing equations. What else do we have here? Draw these lines. Okay, so let's figure this out. Draw these lines. First line is y equals to 1. I think we can do all of them on just one graph, on one system of coordinates. We'll just draw it here. Remember, x is always horizontal line. X is a horizontal axis and y is a vertical axis. Let's put some labels on them. And the first line is y equals to 1. So we know that y equals to 1 is here. This is y equals to 1. But what does it mean? Why is it a line? Well, it turns out that if you think about it as of a line, then you can say that y equals 1 everywhere here. So the point is x can be anything. We don't care about x. X can be 1, 2, 3, 4, 5, whatever. But y always should be 1. And this is the way to show it. Y equals 1 is the line here. It touches the point where y equals 1, and then it goes all the way like this in both directions. So this is the line. Wait. This is the line y equals 1. Then we have y equals -3. So also -3 is here. So we do the same line, but now it touches -3. Y equals to -3. X equals 4. So when it comes to x, the line is actually going to be vertical. So x4 is here. So again, we can just tell ourselves x is always 4, but y can be anything. Like x is 4, but y can be anything it wants to be. 1, 2, 3, 4, whatever. You just care about x to be equal to 4 all the time. So this is the line. Let me write it here. X equals 4. And as for x equals 0, okay, so x equals 0 is here. This one can be a bit tricky, but again, x equals 0, y can be anything. You should think like this. Y can be anything it wants to be, but x is always, always, always going to be 0. So this is our line, x equals 0. Okay, and I think there's one more thing. Okay, oh, this is actually sequences. Let's think about sequences. So again, this is just an introduction to sequences, but you will see more of them later. Way more of different sequences. There's going to be a really hard ones in a couple of years. But right now we only have to figure out the term-to-term rule and next two terms for these sequences. So we look at the first one. So what happens here is we go from 7 to 18. Then we go from 18 to 29, then to 40, then to 51. So what we do is we add 11 each time to get to the next point in the sequence, to next element of the sequence. So the rule for this sequence is add 11, and the next two elements, so 51 plus 11 equals to 62, and then 62 plus 11 would be equal to 73. So next two elements are 62 and 73. Then here, okay, so here what we see is the sequence is actually decreasing all the time. It goes from 10 to 4, and then to -2, -8, -14, and so on. So what happens here is we subtract. And what do we subtract? We subtract 6 each time we work with this sequence. So the rule is subtract 6. And next two terms, let's figure them out. So we do -14 minus 6 equals to -20, and then -20 minus 6 would be equal to -26. So this is our next two terms for this sequence. So -20 and -26. Okay, last one can be a bit confusing. So you can think, if you look at the first action, you can think, okay, this is probably +3, right? Not really. No, this is not +3 sequence. I mean, only from the first action you can judge it like that. But if you look at the next action, it's actually +6, right? And the next one is +12. So what exactly is going on here? What's happening? So what is happening is actually multiplication. So each time we double our elements. So actually we do ×2. So this is not addition and not a subtraction. This is a multiplication. So the rule is multiply by 2. And the next two terms, let's find them. Let's find next two terms. So we do 42 times 2, which is equal to 96. And then we do 96 times 2, which is equal to, what is it equal to? 192. So 96 times 2 is 192. And this is our next two terms, 96 and 192. Okay, that's it for sequences, and also that's it for this chapter. We have one more for this lesson. Interesting chapter, symmetry and transformations. Let's talk about it. So again, the summary. First, you should know about lines of symmetry. So what are actually lines of symmetry? Lines of symmetry is such a thing that when you fold a shape, it fits itself perfectly if the line you fold it in is a line of symmetry. So let me show you an example. Let's say we have this piece of paper like this. So we can try to fold it, or maybe like this, or something like this, right? But it's not gonna fit itself. But look at this. If we fold it here by this line, this shape, which is a rectangle, this shape is going to actually fit itself perfectly. And so what else can we do? We can actually fold it also like this. We can try and fold it like this, which will also give us two exact halves of this shape. So again, we can do like this, or we can fold it also like this. Maybe you will think that what else can we do with this shape? We can maybe fold it like this or something. Well, we can try. You see, we can try this, but this is not a line of symmetry because you see it does not fit itself perfectly. So this, like this is not a line of symmetry. Or you see here, this is not our line of symmetry. So this is a line of symmetry, and this is a line of symmetry. But otherwise, it's not a line of symmetry. There's two of them actually for this case. Okay, so what we have to do is we have to copy these shapes and we have to draw in lines of symmetry for them. Let's do it. Okay, so first one we have, I don't think I will copy them, we're just gonna draw here. So first we have this little cute heart, right? And what is the line of symmetry for this heart? I think if we fold it like this, if we fold it along this line, it's going to fit itself perfectly, like this. Next we have a triangle, which seems to be an isosceles one. So for isosceles triangle, line of symmetry is here, like this. Again, it fits itself, right? Two parts, they are ideally equal to each other. Square is actually a bit tricky. It has a lot of lines of symmetry. So first one is obvious. It's like for a rectangle. So first one is like this. Then second one is like this. But square also, if you fold it by diagonals, it also is going to fit itself. So be careful about that. It also fits itself like this. So a good way to practice this is you can actually take the scissors. You can cut out these shapes, right? I can make a square out of this probably. And you can practice by yourself by trying to fold these shapes. That's the way to practice this topic. And also another diagonal, like this, is going to give us a perfect fold. Next shape is even more tricky. We can fold it like this. And we can fold it like this. And we can also fold it like this. It's also going to be a line of symmetry. And also we can fold it here. And again, this is going to be a line of symmetry. So there's 4 lines of symmetry for this shape. Okay, and next one. What do we have here? Okay, this is about mirror line. Another kind of transformation is reflection. Draw the image of the shape after reflection in the mirror line. So how do we do this? So the reflection has to be, again, a perfect copy of the shape, but the direction is going to be changed, just like my hands here. They're a reflection of each other, kind of. So let's figure this out. So the property of reflection is the distance from the point. Let's call it. Let's name it A, B, C, D. So if you reflect the point A, the distance from point A to mirror line should be the same as distance of reflected A to this mirror line. So this is where our reflected A should be. And reflected D is going to be here. Reflected B, you see it's two cages away, right? So reflected B is also going to be 2 cages away. This is reflected B, and reflected C is going to be here. So our reflected shape is going to look, I would do a fill in. This is what our reflected shape is going to look like. This is reflected C. Next one, we have another shape. Let's name it again. Let's name it A, B, C, D. Sorry, A, B, C, D, because I have no imagination. I name all my shapes A, B, C, D. So A, we go here. And then to other side also should be the same distance. You see, exactly 1 cage, exactly 1 square. So this is A reflected here. B reflected is 2 cages away, just like B. C reflected. Sometimes you don't have to draw all the points, you can kind of guess where they're going to be, especially if there's a lot of them. And this is our reflected shape after all, yeah. Something like this. Okay, that's how you do the reflection. Next we have translation. Describe the translation of PQR to STU. Let's figure this out. So what happens is we have to, this is absolutely the same kind of triangle, just 2 times. So what happens, I'll try to show you. Let's say we have a triangle here, and then what we do, we just copy this triangle, like this, I just copy it, I paste it right here, and then I move it. This is what translation is. It's just a movement of a shape. So what we have to do to describe the translation, what we have to do is we have to find how far exactly each point has moved. So let's look at the point U, I would say. Let's pick the point U. So point U becomes point R after the translation happens. So let's figure out what happened to point U. So we can see that point U, it went 1 step down, and then it went 4 steps to the left. So again, we go 1 step down and 4 steps to the left. Or we can write it shortly as 1 down. You don't have to describe every point because they're all actually going to be the same. So we can check S to P, right? So again, it goes 1 down and it goes 4 to the left. So they will all have the same kind of movement with the first point. So 1 down, 4 left. This is how we would describe this translation. Next we have rotational symmetry of shapes. Let's figure this out. And for rotational symmetry, we have to normally have a center of rotation, but in this case the center of rotation is the center of a shape. So it's a no-brainer in this case, but sometimes it's getting complicated. Maybe later you will see some more complicated examples. So how do we do rotation? Again, I will show you an example with a triangle. Let's say we have this small triangle, and again, we lay them on top of each other. And so what we do is we rotate this triangle, and then we count how many times during a full rotation it's going to fit itself. So order of rotational symmetry is always at least 1, because at least when you start the rotation, it's going to fit itself 100% certainly, right? So when you start it, it fits, and then you rotate it, rotate it, rotate it, rotate it. It does not fit itself at all during the rotation. Like this, it goes like this, like this, like this. And finally, we are back to the start. So we can say that for this triangle, the order of rotational symmetry is equal to 1. Let's look at some of the shapes. I think I should start with B because it's going to be easier to draw. I will just draw a B here, and I'll try to show you how a B works. So in B we have this small kind of triangles on the end of, yeah, it's a weird shape. Okay, I'm sorry for this ugly shape. I hope it will work out for what I need it for. Okay, so let's fit it, and let's rotate it. So, okay, so we start, there's already 1, so 1 time it fits. Oops, I have to do it again. 1 time it fits. Then we keep rotating it. Then we rotate, rotate, rotate. Here, it should fit itself. So it should be 2. Then this should be 3 if it was a normal shape, but it's a bit ugly because of my drawing skills. And then finally we go 4. So this is 4. For this shape, it's going to begin 1, 2, 3, 4. So order of rotational symmetry for this shape is 4. So for B, for B it's going to be 4. For A, maybe you can see that because there is 3 triangles, so each time you rotate it, it's going to fit those triangles. So like it's going to be 1 time, like this, right? And then you rotate it like this, it's going to be 2nd time, and then it's going to be 3rd time here. So for this, the order of rotational symmetry is 3 for A. For C, for square, order of rotational symmetry is 4. And for D, order of rotational symmetry is 3. So again, let's imagine we have this triangle. We rotate it. It's going to fit itself once, and then twice, and then finally a 3rd time, like this. So 3, 4, 4, 3 for rotational symmetry. Okay, and finally, so the hardest question is the last one. Now we have to actually rotate the T shape 90 degrees clockwise about the center of rotation O. Let's do it. Let's do this. How do we rotate the shape? So to rotate the shape, we have to, and so clockwise it means like this, in this direction. There is clockwise, and there is anti-clockwise, which is the opposite direction. And in this case, it's clockwise 90 degrees. So if, for example, if we had a line like this, if it would go 90 degrees, this line would happen to be here. So what we have to do is we have to rotate each point. I think I will, I think I will name them. So we go A, I think I have to make it bigger, A, B, C, D, E, F, G, H. Like this. So let's start with point A. Point A, we have to draw a line to the center from point A. This is our center of rotation. And then this line is going to rotate 90 degrees like this. So point A rotated is going to be here. We can draw it here already. So this is point A rotated. Let's draw it here, yeah. Point B rotated, so look at this carefully. Point B rotated, we still can see what's happening. It's going to be, so if we rotate it by 90 degrees, like this, point B rotated is going to be here. And for C, I will have to show it to you more carefully. Let's do a C. So C, we draw this projection to C. And here it becomes kind of hard to rotate this line. So the way we should think about it is we should think about it as of a hypotenuse of a triangle. So let's draw this triangle. Let's say we have a triangle here, like this. And what we have to do now is we have to rotate this whole triangle by 90 degrees. So that we can see the hypotenuse. So this side is going here, right? This is going to be this side, and this side is 4 cages long. 1, 2, 3, 4. So we can draw it here like this. Then this side, it has to be next to that side, so it has to be here. Again, 2 cages long like this. And finally, our hypotenuse is going to be here. And remember, the point C is on the end of this hypotenuse. So point C is going to be here. This is point C rotated. And from now on, I think you can see what's happening. So this is A, B, C. Then this is probably going to be our D. And then the shape goes like this. Let's draw it. So you don't have to do all the points. Just do a couple of points until you can see where this image is going. Let's draw them. Let's draw them now. Whoops. Wrong tool. So this is, oh my goodness, that looks so terrible. Let me think I will have to erase this. And this as well. And so let's draw it. This is our T rotated. So again, what we did is we rotated it like this. We drew a line from each point to the center of rotation, and we rotated this line 90 degrees clockwise. 90 degrees clockwise for each point. Not necessarily for each point, but as long as you get the image. Where is it going to be? Okay, that's it for this lesson.